Going to wait to see if it's streaming. Okay, so I'm gonna go over Turing complete. I don't really care about the solutions. I'm just gonna. I already did a bunch of the puzzles again, and I'm just going to go over the ones that I've already done, and then probably, like, if there is some time left, I'm gonna try to solve these other ones that are harder. But I think I'm probably just gonna look into the solution, because the main reason why I'm doing this is just to go over the fundamental principles of computing again, to strengthen my understanding. And I don't really care about uh, solving the actual puzzles. And I'm gonna use ChatGPT probably to figure out the solutions and also look for the solutions online. And I'm probably not gonna string myself building anything anymore. I'm gonna come back to streaming frequently, but I'm just gonna do some other stuff. I follow some ideas or whatever, like build random projects, stuff like that. I think this one is very simple. Yeah, so just a signal. Go back. This is the first gate. So it gives you a truth table, and then you have to make it correct. Not sure why it's not showing here. Probably on the other levels, it shows the gates that you solved. This is obviously just an NAND gate truth table. Another NAND gate. This one, I think that shows a relationship between the main logic gates and how they relate to each other. And you can move around. I think it's called De Morgan's table or something like that. You can move around each main logic gate by inverting either inverting the inputs or the outputs. And I think that from most resources that I've seen, they show the NOT gate first. I think so. This is probably the main one, the fundamental one, and then they show the NAND gate after. But I'm not really sure why they do this, because I think that the three fundamental ones, in order to be Turing complete, you need three main fundamental logic gates. Is the NOT, the AND, and the OR. The AND encapsulates the intersection between things. The NOT is the inversion of something, and the OR is the union of the two different things. And with these three main logic gates, you can build any computation you want. I think that's just a property of space-time. That's why it works this way. So here, I think that trying to do the AND gate. Now the AND gate will be just issue. If there wasn't the NOT here, it would be the AND gate. This one I don't remember. Maybe it's the NOR gate. The level long. So this is not the level that they show the Morgan stuff. Oh, yeah, here. This is the law, and you can go, so you move horizontally, no, move vertically by inverting the inputs, and move horizontally by inverting the outputs. So in that case, we are on the NANDs, and then we invert the two, so we go to the NOR, yeah. The solution is the NOR gates. So this is the AND gate, because it inverts the inputs only. This is the OR, I think. No, this is not. So this is the AND. So the other one is the OR. I still have on some, I think on all the levels, I have the solutions to the previous version. So it might be interesting on the other levels to compare. Yeah, so this is the AND. It works there. The other one is the OR. Yeah. It's just the NOT. Here it isn't one of the fundamental ones. Just the way that I solved some of this was by using ChatGPT to derive the answer. And the way that we did this is by it's basically Boolean algebra. So if you have the truth table, you can draw the inputs and the outputs, like the zeros and ones, write the zeros and ones down on the truth table, and then you can build an equation that ends each input row and ORs the rows. And then you simplify that equation, basically, to get to the cleanest form, the reduced form, and then try to find the invariants. So the invariants are things that don't change based on inputs. And then after this, you select the logic gates. But it's still kind of unclear to me how to find the invariants. I think it gets very complicating and confusing. Basically, that's how. Before, the first time I tried to do this, I was like just randomly testing the gates. But obviously this way is a lot better. But it's still kind of annoying because you have to manually simplify everything. So I didn't want to do the work to simplify myself. So I just used ChatGPT for this. And this solution that ChatGPT arrived, I think that this is the XOR gate. So it uses an OR and not. Maybe we should ask ChatGPT to explain again. The XOR is a fundamental one, so maybe it's probably better to try to draw the. I'm using the dot language to write the graphs. Why the...
Start from the object you actually have, a truth table. Nothing else is allowed. Gates are just concrete realizations of Boolean operators. The problem is to synthesize a Boolean function from its extension. 1. What XOR is, independent of gates. Given inputs a b0 1 a bin 0 1 a b0 1. A b equal to not equal top text XOR, a b equal to 1 if a neck XOR, a b equal to equal top. Equivalently. True when exactly one input is true. False when both are equal. That second phrasing already hints at structure. XOR is a difference detector, not an accumulator-like or nor a conjunction-like. And 2. Start from the truth table as a set of satisfying assignments. Truth table. ABSOR 0, 0, 0, 0. The rows where the output is 1R. Equal to 0, equal tune. Equal to 0, equal tune, equal to 0, equal tune. Equal tune, equal to 0, equal tune, equal to 0, equal tune, equal to 0. From Boolean function theory, this immediately gives the sum of products, DNF. A b, ab, ln lot b, lor, lot ln b, a b, ab. This is not a trick. This is mechanically derived. Each one row, a minterm. Minterm equal to and of, literals, matching that row. Whole function equal to or of those minterms. This is the canonical derivation from the table alone. At this point, XOR is already fully specified. 3. Why that DNF is structurally correct. Look at the two terms. A bala not ba, b, A is on while B is off. Ablot a ln b ab, B is on while A is off. These are mutually exclusive regions of the input space. That matters. They never overlap. So or ing them introduces no ambiguity. XOR is literally a disjoint union of cases. This exclusivity is the conceptual core of XOR. 4. Gate cost pressure. Algebraic refactoring. In Turing complete, gates are costly, so you don't want 2 nots, 2 ands, 1 or, unless unavoidable. Now observe a different identity. Ab equal to ab. This is what your solution implements. Let's derive it, not assert it. 5. Derivation of abi alor b lenlot aln b abi. Start from the semantic definition. At least one is true, but not both. Translate directly. At least one is true, ab alor bab. Not both, ablot aln b ab. Combine with and because both conditions must hold. Ab alor b lenlot aln b ab. This is not algebraic cleverness, it is a direct logical decomposition of the English meaning of XOR. 6. Why this expression matches the truth table. Evaluate the two sub-expressions separately. Case analysis.
I wonder if I can do this. But it would have to be, it would need to be both, I think. Yeah. So it ends up being the same. Let's see if I have the solution to the old thing. So this is the one that I did intuitively the first time that I played this. I didn't know anything about. It's still hard to solve, even if you know a lot of stuff, because I have to think about the truth tables. As I was listening to the answer, I was thinking about in terms of like space and sets. Might be interesting to do that on SkyDraw as well, because I think that it will clarify things. So like it has been becoming, that's the right way to say it, more clear on my mind why the logic gates work in the way that they do and why they allow calculation and computation. I think it's basically properties of space and time. But time is just a measurement of the frequency in which space changes, obviously. But I think that this is the reason why it's probably a good idea to visualize on sets. Because if you think about it, like all these main fundamental 3 gates, they encapsulate the relationships of space-time. So you have in order for space to exist, you need the observer and what's being observed. And you need a limit as well. So basically, like the end is going to be the intersection, which is the boundary between things. The R is the relative connection of things, like the composition of two things into one thing, because it's all dependent on the scale of observation, obviously. So I think those two things are the fundamental properties of the connection between things. So the end happens at the perceived boundary between things, and the R is like the relative union between them. And the not is obviously the negation of it, like the opposite of it. There's the principle of gender. And based on this, you have, like, mathematics is just the symbolic encoding of these relationships relative to an observer. So the reason, this is something else that I was thinking about some time ago. Basically, the reason why you have square roots is because the numbers are symbols that encode the relationships in space. So whenever you have a square root, would be like the decomposition of a higher scale into a lower scale by extracting its fundamental fractal patterns. Yeah, so when it comes to the XOR, I was thinking about, like, if you think about the logic gate operations, what they're basically doing is shaping the space, the nature of space, the topology of space, based on the causal inference of time, let's say, because the input is obviously going to add causality to the situation. So the logic gate structure is the topology of space, and the inputs, the signals, are encoding the causality of time. So what's happening is you have, like, I think that you can derive based on the relationship between the gates that are connected to the inputs. You can see how the space is changing based on the connection. And this allows you to have a more intuitive understanding of what is going on when the logic is happening. But it might be a waste of time to draw this on SkyDraw. I was trying to visualize on my mind how this works in practice. And obviously the solution was bad. Let's see what I did. But it's basically the same thing with just an extra step, I think. Yeah. Go back to the best solution. So the end would be this section here. Not sure how to draw this. Maybe it's better to write. And this here, the R is the connection between them. The R is outside everything, basically. And these things are always changing because obviously there isn't a fixed point. Actually, there is. This is another thing that I was contemplating a lot, which is fixed points and their relationship with recursion and all these problems as well. And I was talking to GPT about this as well. I was saying that you need at least 2 fixed points. So fixed points are like stable equilibriums on a dynamical system. So you need at least 2 in order to have information. And that's why in order to have memory, you need to have a loop on Boolean algebra. But it can't be all loops. That's what I was asking. Because if you have no loop, then you don't have the fixed point. If you have only one, only one fixed point, then you have a convergence, and there's no distinction. So in order to encapsulate information, you need at least 2 fixed points. So and the not would be like the abstraction or imagination. So the negation of the relationship between them, which exists like on a quote unquote another dimension, but not really, but kind of. So I think what is happening here, if you think about it, is like one input. Yeah, so these two inputs here are gonna select this, so this is gonna be filled, this region of space, I think. But then the not is gonna exclude this region, and it's gonna take either this or this. This would be like A, and the other one is B. So I think that's what's happening. So when you have the circuit here, like the output you're gonna get here is gonna be these two regions of space. Because the first one filtered for this one, and the other ones are the not is inverting basically, so you get the other ones. And this one will be like the full thing. So on this AND gate, you're getting the full thing, and this and this. And both of them have to be true pass. The question is like, what does this mean? And this is what makes it hard to think about, because you have to think about the variations of the inputs and how they're going to impact this. Because obviously the AND is only going to work if both inputs are true. Now what does it mean they are not? Like what happens? I think that's what I should try to ask GPT. It makes sense when the condition is true. Then it makes it easier to think about the output. Like what region of the... So the logic is like a filtering on space that creates the topology of computation. But then, like, what happens when what doesn't go through? So I think so. This is the problem, because there are levels. It gets like very complicated very fast, because you're gonna have the other AND gates, and the other AND gate's gonna select for this region of space, which is the exclusion of the other one. And this region. So it would be like a bigger circle. Yeah, so I think this is what it means, because you have another circle here, encapsulates like both of them. This would be the final ends there. This is the reason why it works, because the first input is filtering like this region and this region. It's going to be the output if this condition is true. And the second one is obviously the sum of them, so it's the entire region. So when both conditions are true, it's going to select either one of them, depending on the input state. I don't know if this makes any sense. Yeah, because the not gate negates there. So yeah, when either one is false, it doesn't pass, but then the not inverts, so it means that they're gonna be on. which means that it's gonna be true. Yeah, so it's basically selecting this two here based on the NOT gate. I think it makes sense. But what does the AND enforce? I think the AND enforces the either one property. If it was an OR gate, then it would always, no. It's still kind of hard for me to think about this.
Analysis. Abba B. Notice the roles. Abelor Bab excludes the 0-0 case. Ablot Alen B. AB excludes the 1-1 case. Their intersection leaves exactly the XOR rows. So XOR is literally input space subtraction. All non-zero inputs minus the fully on state. 7. Mapping this to your circuit. Your circuit. And gate computes Abelan Bab. Not gate computes Ablot Alen B. Ab. Or gate computes Abelor Bab. Final end intersects the two conditions. This matches the formula exactly. No redundancy, no coincidence. 8. Why this solution is optimal in the game. Under typical constraints, you need at least 1 negation, XOR is not monotone. 1 conjunction, 1 disjunction. The expression ab, alor b, landnot, alen b, ab, uses or 1 and, not 1 and. That's minimal unless you're allowed NAND, nor primitives. Any implementation of XOR must distinguish equality versus inequality. Detect coincidence, both 1. Detect presence, at least 1. Those are irreducible information requirements. 9. The hard conceptual part, this is where people stumble. The difficult leap is realizing XOR is not a special gate, it is a constraint on 2 simpler predicates. Predicate 1, something happened. Or, predicate 2, too much happened. And, XOR equal to allow predicate 1, except when predicate 2 fires. This is why the construction feels indirect. XOR is defined by exclusion, not accumulation. 10. General principle, you should extract. From truth table, optimal circuit. Identify which regions of the input space should survive. Describe those regions as coarse predicates, or, and. Subtract forbidden regions using negation. Intersect what remains. That exact reasoning scales to adders, comparators, parity circuits, state machines. XOR is just the first place where non-monotonic logic becomes unavoidable. If you internalize XOR as allowed minus forbidden, the circuit stops being mysterious.
Trying to think about how does the inputs relate to the structure of the gates. I think I'm starting to clarify a lot more on my mind how it works fundamentally speaking. As I think that the inputs encode causality, and the logic gate structure encodes the structure of space. So can think about computation as an observer, how an observer views space at a given time, because the time is going to determine the clock, which is going to determine the input state. Yeah, so it's basically encoding the state of space based on voltage differential that determines the arrow of time based on the state machine, which is the topology of the logic gate structure. And this creates mathematics. So I used to think that mathematics is more fundamental than logic, but now I realize that logic is more fundamental. And I think it works exactly in the way that the computers work. The main difference between computers and mathematics is that computers use memory, mathematics don't. And computers, they encode the higher resolution of mathematics because it's down to the booleans. Mathematics is a compression of the Boolean algebra, I think. I think it's worth spending more time. I'm trying to think about whether or not I should ask ChatGPT for, like, based on this stuff. The thing is that kind of hard to translate into words the diagram here, but trying to think because there's also this thing about invariants that ChatGPT talks about a lot, which I also think that makes a lot of sense. Which are invariants are the things that don't change according to the inputs. It's basically the fundamental nature, let's say, of the structure. But it's always very confusing to me and kind of hard to grasp what it means. The reason why like this view here is very interesting is because it clarifies the relationship between the symbols in mathematics and in space, and objects in space. And XOR is used for sum or for the arithmetic logic unit. This is one of probably the most important gates. So I'm trying to think about what this means. If I remember correctly, full adder, there is a level about the full adder next to after this, but it's basically XOR gate connected through an AND gate for the carry. And I'm trying to think about so like it becomes more clear when you think about it like this, because what's basically happening is that you're composing a different object based on the structure of space. So each XOR selects one of these regions here, and because they are connected with other ends on, so it's like this structure is copied, and the combination of them allows you to compose a different region, different symbolic representation of space, which is the calculation basically that is happening. I think that's what's going on. I'm just gonna move on to, I don't think it's worth it to, maybe on another level. I was gonna ask about invariants on this level, but maybe on another level it makes more sense. Ask what is the invariant here. I think on the memory levels, it becomes more, it makes more sense to ask about this. So this one also, oh, so this is the 3-AND gate, very easy. Those are showing how to build an AND gate that has 3 inputs. The bigger AND gate, very simple. And the same for the OR gate. So this is an inverted XOR, basically. The XNOR gate, yeah. So if you remember the Morgan table there, you just invert the outputs. The other is the same, so it's gonna be the XNOR gate. So this side is memory related, and this side I think is arithmetic related. Odd number of signals. This is kind of like a binary counter. Like it reminded me of a binary counter or something like this because you can see the frequency of the inputs here. Is changing by 2 on each input. But I don't think that this is the binary counter. The binary counter comes after. It's just a similar thing, I think. Try to visualize on my mind this diagram here. Like if you think about it, like fundamentally speaking, each logic gate is gonna be this abstraction here. And I think that this is the case because this is a exemplification of the electromagnetic field. So everything works based on the principle of the electromagnetic field, and it's based on the flow towards a counter space, or potential, or voids, or whatever you want to call that, which would be in the middle of the magnet, but not really in the middle because it's outside of space. So it's everywhere and nowhere at the same time. And the perspective of, I believe now that the thing is kind of hard because everyone that studies an area a lot tends to think that the universe is based on that area. So I don't think that is fully that. I don't think that the nature of reality itself is based on computation, but I think that the nature of space-time is based on computation. So you can think about like the boundaries between things as being the frequency of the computation of the observer, and space is a holographic projection of the observer. So I think that what is happening with the reason why computers can simulate reality is because we are using the geometry of the hardware to create this symbolic representation, which is based on the voltage difference that creates this changing space that you can visualize on the screen through the pixels. So I think that what is happening is that each gate is going to follow this fundamental pattern. The fundamental gates are about this relationship here always, because you have the opposites, which is our left and right, the two poles of the electromagnetic field. Then you have the intersection, which would be on the counter space, and the computation is going to be the flow between the two that manifests itself on space. So what you see on space is the relationship between, is the interference pattern of these relationships here. So when you have these gates fluctuating across each other, this creates the illusion of distinction, which are the objects that exist. But I think that what these circuits are doing is connecting this fundamental pattern through time based on the inputs. So the input determines the flow of the signal, and the time determines the state of the whole structure. And what is going on here would be like this first gate is selecting either one of these based on the input. It's basically filtering this region of space, and this other one, this one is hard because I think that's when it gets confusing. Because like this one is connected directly on the input, but then like before this input is kind of like a black box. It's hard to think about what does it mean. I think I'm struggling the most to make sense of how the inputs are going to shape the structure. Because when you think about the gates, you're thinking about all the inputs simultaneously. So when I say that's going to filter A, I'm already thinking about like all possible. It's going to filter for A when the inputs are 0, 1, 0, 0. Or 1, 0, 0, 0. The other two doesn't matter. If we draw the, what's here? This. So it would be as if this thing here, kind of like here. So it receives one input from here, and the other one from there. So what does that mean? How can I make sense spatially of what the output means for the gates? So I think that, so from this standpoint, it's either going to be this one or this one already. So what does it mean when this because this one would be another XOR, so that's why hard to think about. And so I think that when this input is 1, it's going to select whatever one this one filtered. That's what it means. The XOR is going to filter again for both either this one or this. So this inputs here, it just determines which one is being selected, I think. Actually, I'm not really sure about this. Yeah, but the question is how to ask ChatGPT in a way that is going to allow me to clarify. It's very confusing because like the inputs, the output is going to change. Like when I say it's filtering, it's not really true. Like let's assume this is the XOR here. That would mean that if this is on, it's only going to pass the value if this one is off. But if this one is off, it means it didn't select either one, I think. I'll be right back. Into the bathroom. I think about how to ask ChatGPT in a way that allows me to clarify this and what is happening spatially. Maybe what is the relationship between the inputs and the space that it selects for. I'll be right back. Okay, I'm back. I think what I'm gonna ask is, so you can think about logic gates being the topology of space and inputs as being the causality of time. Having a hard time trying to clarify or understand how the variance of inputs change the perceived outputs from from logic gates connected to each other. So for example, 3 XOR gates are 4 inputs, 1 outputs. First inputs are connected to first XOR. Second, three inputs are connected. One to first XOR and the other the second. Third and fourth inputs are connected. One to the second and fourth the third. Trying to reason about the perspective of the signal on the second XOR. How does it perceive the structure of space based on the input state? You can think about an XOR as being a filter on space that selects for either A or B, where A is the excluded union on the left side and B is the excluded union on the right. The thing that is kind of hard is because I can't really, there's no any easy way to draw the diagram there. I'm not sure if he's gonna understand what I'm saying, but hopefully. But what happens when the output is false? From the perspective of the second XOR, does it treat the previous input as a black box? And what does this mean? Its output. I think what it means is that when the first XOR is, when it doesn't hold true, from the perspective of this XOR, it means that it's going to select whichever space it has. I think it's starting to become more clear. So when this doesn't pass through, it doesn't act as a filter. So like from the perspective of this one, it becomes a black box because there is no input here. And then this input is going to be the one that determines whether A or B from this XOR is going to go through. But let's think about the other case. Let's say this is true. This passes, so either selects B or A to go here as the input. What happens here when this is 0? That means that it's going to have to pass. But then, like, what is going on here? I think it's just going to propagate A or B. Because it's not really different regions of space, I think. Because like this is just an abstract pattern that I'm using. It's not like that there's different A or Bs. It's just only one A or B because there's only one input, I think. I think that this is gonna depend on the structure of on how you make sense of the impulses, like the translation between Boolean algebra or Boolean numbers into decimal numbers, which is like an human abstraction. But I do think that it is grounded on fundamental principles as well. because you can think about numbers. The way that I think about numbers is like a scale. So numbers measure scales. They encode the scale of space into an abstract symbolic representation. And that's why you have from 0 to 9, which is a property of mathematics, because it is in a specific semantics that encodes the logic of space. But you can have different variations of that, and that's why when mathematics evolves and expands, you have different symbols because they encode different relationships at different levels. Yeah, so I think that the meaning, so like you can think about A and B as always being the same. What's gonna derive the meaning of what that means in space is gonna be the logic gate that determines the relationship between the Boolean algebra that is gonna create the decimal representation. Because that's how the memory is gonna make sense of what is going on. You're just gonna ask this. So from this point here would be like propagating the value. So when this input is on, this has to be off for you to pass through. Let's assume that is off. That means that whatever was selected here is gonna propagate to the third XOR. So this one doesn't create another A or B. It just propagates the value from this one, the original space from that one, until it reaches the output, which is going to determine which of these spaces is selected. And then the meaning is going to be derived based on the way that the logic circuit that is connected to these other circuits it's called EEPROM, combinational logic. It's basically these truth tables here, and is deterministic because you have a predefined set of inputs that are going to have a predefined set of outputs, and they are connected to different components of the computer. So this is like the control logic. Control logic is just different parts of these logic gate systems connected to each other through wires that propagate the signal, and they are going to be encoded by these Boolean algebra tables, which are hard-coded on the hardware. This is like how the BIOS is created. So it's like a predetermined set of Boolean algebra that is going to determine how all the circuits of the hardware are connected to each other. And this is going to generate a deterministic transition of states based on the Boolean table from this combinational logic, which is predefined based on the EEPROM. And this relationship is going to determine how the meaning of the relationship between the parts of the computer makes sense. It's kind of trippy to think about because they're both Boolean algebra, but it's like different. It's because the tricky part is the way that the computer makes sense. So I guess this is something that I could ask as well. I think that the control logic is going to be the one that determines what the meaning of this propagation of the values is. So what it means for H to propagate to this place. Eventually is going to, like from this circuit here, which is represented here, is going to reach the output. And this output is going to be an EEPROM, which is this, you can think about it as a massive truth table of values. Like this would be one system, then you would have other stats like this on other parts. And they all connect to this EEPROM, which is a giant table of booleans. And then the states from each of these things is going to determine the next state of the computer. And I think that the way that you set up the the control logic of the EEPROM is what determines how the outputs are gonna make sense for the rest of the computer. And then the fluctuation of states is going to be connected to the memory, and the memory is going to be a symbolic representation of what's happening. So like a simulation, because you're encoding the topology of space into the voltage differential of the input and outputs of the circuit. So it creates a hologram. I think that's what's happening. So like the logic gate structure is connected through different parts, different regions of space-time that have different voltages because they exist at a different equilibrium point, which is the counter space of the electromagnetic field. It's like a recursive pattern because it's a holographic. And this difference in voltage creates the time of the clock cycle, which is a loop. It's going to be the fixed point of the computer, or the fixed points. The fixed points are going to be memory. So memory is like a stable, is a relative stable attractor state of the hardware that encodes the information. Because otherwise it would be too chaotic to remember. So what you have is fluctuations of fixed point states that create the simulation. Like computers, I think that they are, and it's probably most likely the way that we operate as well as human beings. But the main difference is the substrate, because we compute using water, and computers compute using silicon. I think that is fundamentally different, but the patterns are the same. The counter space is a paradox. Imagination is the imaginary numbers, and the real is the space. Imagination is asymmetric, space is symmetric, so it creates a fluctuation of time. It is a holographic projection.
I'll stay at the level you're aiming for. Semantics is structure, not gate folklore. Stop thinking in terms of signals flowing. That metaphor breaks exactly where you're getting stuck. A combinational circuit has no temporal causality internally. There is no earlier or later gate in the logical sense. The entire circuit defines a single Boolean function. F0, 1, 4, 0, 1, 0, 1 for right arrow 0, 1 F0, 1, 4, 0, 1. Every gate is just a factorization of that function. Time only exists at the boundary, inputs change, outputs settle. Inside, there is only constraint satisfaction. So from the perspective of any XOR, nothing arrives from the past. It is given two Boolean variables, one may itself be a compound expression, and it evaluates its predicate. 2. What a gate perceives formally. Take the second XOR you're focusing on. Let inputs.
So frequency doesn't change the structure. It changes how dense the space seems to be from the observer perspective. Because the clock cycle is always, like the clock cycle is not going to change the structure of the gates. It's just going to change how frequently the state changes. And that frequency, I think, is what is density. So that connects with the spirituality side, the David Hawkins scale of consciousness. I think just different gradients of density. The higher the density, the more solid you're going to be. Because there's higher frequency, I think. Might be the other way around, but I think that it makes more sense to be higher frequency. Actually, maybe not. Maybe it's lower frequency because it changes less often. In relationship to the observer, because everything collapses to, there's only one observer, and that observer is infinite, and there's many observers at the same time. But it always collapses to only one observer, because if it wasn't like that, you wouldn't have equilibrium, like relative equilibrium. So this is the reason why I think as well you need at least two fixed points to have information, because it's the encoding the relationship between observer and what's being observed. If you only have one fixed point, you only have the internal side and not the external, or vice versa. So you need two in order to have experience, because you need two to have perspective. And the fluctuation of them, which is computation, is what's perceived as time, which is perceived as one-way street because it is dependent on the nature of the observer. Like it's a property of the computation itself.
Inputs be x1, x2, x3, x4, x1, x2, x3, x4, x1, x2, x3, x4. Suppose the wiring is 1 equal tox. From the perspective of the second XOR, its left input is the Boolean function. G1, x1, x. Its right input is the primitive variable. x3, x3, x3. That's it. There is no memory of structure upstream. The gate's entire world is 2 equal tog. This is not an implementation detail, it's the abstraction boundary. Free. Black box is not an approximation, it's exact. Yes, the second XOR treats the previous output as a black box, because Boolean algebra is referentially transparent. A Boolean expression can be substituted for a variable without changing meaning. A B sys just FC, A O plus B, O plus C. The XOR gate does not know why its input is 0 or 1, only that it is 0 or 1. This is not loss of information in the global sense, the information is preserved symbolically in the compose function. 4. What XOR actually does to space. Your topology of space intuition is good, but it needs sharpening. Think of the Boolean cube. 1 input, line segment. 2 inputs, square. 3 inputs, cube. 4 inputs, 4 cube. Each XOR gate folds space along a parity hyperplane. For 2 inputs. A, B. So XOR partitions space into even parity region. Odd parity region. This is not a filter selecting A or B. It is a quotienting operation. Collapse all states with the same parity into one equivalence class. 5. What happens when XOR output is false? Important point. XOR equal to 0 does not mean nothing happened. It means equal to. So from the second XOR's perspective, if G1 equal to 0 G1 equal to 0 G1 equal to 0, then X1, 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 and X2 Tech2 X2 are equal. If G1 equal to and G1 equal to 1 G1 equal to, then they differ. That single bit encodes a relation, not a value. So the second XOR is not operating on raw inputs anymore, it's operating on a constraint summary of upstream space. 6. Why chaining XORs works, associativity. XOR has a crucial structural property. A B C equal to A, BC, A O plus B O plus C equal to A plus, B plus. This is not algebraic trivia. It means XOR is associative. The order and grouping of space-folding operations does not matter. So your 3 XOR chain computes 2x, 2x, 3x, 4x, 1O plus x, 2O plus x, 3, which is global parity. Each gate does not care where the bit came from. Only toggles parity if its input is 1. 7. Perspective of the second XOR precisely. From inside the second XOR. Input 1, a bit encoding parity of x1, x2, x1, x2, x1, x2. Input 2, a raw bit x3, x3, x3. Its rule. If x3 equal to 0, x3 equal to 0, x3 equal to 0, pass parity through unchanged. If x3 equal to 1, x3 equal to 1, x3 equal to, invert parity. That is the full causal story. No spatial awareness. No topology. Only parity algebra. 8. Why false output is not absence. When the second XOR outputs 0, it means. Which implies. X1. That is a global constraint on 3 inputs, not a local failure. So false is not empty space, it is coincident parity. 9. The deeper abstraction you're circling. What you're really seeing is this. XOR gates form a group operation over Z2 math B Z2 Z2. Each gate composes a homomorphism. The circuit computes a linear form over GF2. So the space is a vector space. The signals are basis coefficients. And the gates implement linear maps. Once you see that, the black box behavior stops being mysterious. It is exactly how linear operators compose. 10. One sentence summary. The second XOR does not perceive structure or history. It receives a single bit encoding an equivalence class over upstream space and composes it with another bit under parity. False is not nothing. It is the statement the accumulated parity so far is even. That is the invariant being preserved.
For once is parity. Not sure if I understand what it's saying. States are condition of being equal. Like what does it mean? I might have to read this again, the response again. What does it mean for? Or even or odds? I'm gonna read this again. I think it doesn't understand the place I'm coming from, but it's coming from a different angle. I want to understand what it's saying exactly. Not sure if it's saying that the gate, like this circuit's gonna find if it is an odd or even signal.
I'll stay at the level you're
Yeah,
aiming for.
odd number.
Semantics is structure, not gate folklore. Stop thinking in terms of signals flowing.
So this is gonna tell whether or not the signal is odd.
That metaphor breaks exactly where you're getting stuck. A combinational circuit has no temporal causality internally. There is no earlier or later gate in the logical sense. The entire circuit defines a single Boolean function. F01401, 1 for right arrow. Every gate is just a factorization of that function. Time only exists at the boundary, inputs change, outputs settle. Inside, there is only constraint satisfaction. So from the perspective of any XOR, nothing arrives from the past. It is given two Boolean variables, one may itself be a compound expression, and it evaluates its predicate. 2. What a gate perceives formally. Take the second XOR you're focusing on. Let inputs be x1, x2, x3, x4, x1, x2, x3, x4, x1, x2, x3. Suppose the wiring is 1 equal talks 1 x2. From the perspective of the second XOR, its left input is the Boolean function g1. Its right input is the primitive variable x3, x3, x. That's it. There is no memory of structure upstream. The gate's entire world is g. This is not an implementation detail, it's the abstraction boundary. 3. Black box is not an approximation, it's exact. Yes, the second XOR treats the previous output as a black box because Boolean algebra is referentially transparent. A Boolean expression can be substituted for a variable without changing meaning. Abby. The XOR gate does not know why its input is 0 or 1, only that it is 0 or 1. This is not loss of information in the global sense. The information is preserved symbolically in the composed function. 4. What XOR actually does to space. Your topology of space intuition is good, but it needs sharpening. Think of the Boolean cube. 1 input line segment. 2 inputs, square. 3 inputs, cube. 4 inputs, 4 cube. Each XOR gate folds space along a parity hyperplane. For 2 inputs. A equal to 1a. So XOR partitions space into even parity region. Odd parity region. This is not a filter selecting A or B. It is a quotienting operation. Collapse all states with the same parity into one equivalence class. 5. What happens when XOR output is false? Important point. XOR equal to 0 does not mean nothing happened. It means equal to. So from the second XOR's perspective, if G1 equal to 0 G1 equal to 0 G1 equal to 0, then X1, X1, X1 and X2 X2 times 2 are equal. If G1 equal to 1 G1 equal to 1 G1 equal to, then they differ. Single bit encodes a relation, not a value. So the second XOR is not operating on raw inputs anymore, it's operating on a constraint summary of upstream space. 6. Why chaining XORs works, associativity. XOR has a crucial structural property. AB equal to. This is not algebraic trivia. It means XOR is associative. The order and grouping of space folding operations does not matter. So your 3 XOR chain computes. S1 X2, which is global parity. Each gate does not care where the bit came from. Only toggles parity if its input is 1. 7. Perspective of the second XOR precisely. From inside the second XOR. Input 1, a bit encoding parity of x1 x2, x1 x2, x1 x2. Input 2, a raw its rule. If x3 equal to 0, x3 equal to 0, x3 equal to 0, pass parity through unchanged. If x3 equal to 1, x3 equal to 1, x3 equal to, invert parity. That is the full causal story. No spatial awareness. No topology. Only parity algebra. 8. Why false output is not absence. When the second XOR outputs 0, it means 1, which implies that is a global constraint on 3 inputs, not a local failure. So false is not empty space, it is coincident parity. 9. The deeper abstraction you're circling. What you're really seeing is this. XOR gates form a group operation over Z2 math B Z2 Z2. Each gate composes a homomorphism. The circuit computes a linear form over GF2. So the space is a vector space. The signals are basis coefficients. And the gates implement linear maps. Once you see that, the black box behavior stops being mysterious. It is exactly how linear operators compose. 10. One-sentence summary. The second XOR does not perceive structure or history. It receives a single bit encoding an equivalence class over upstream space, and composes it with another bit under parity. False is not nothing. It is the statement the accumulated parity so far is even. That is the invariant being preserved.
Hey, what's up, Denzel? How are you? I think I kind of understand what it's trying to say. It's basically encoding all numbers. I use the filter terminology, but it's basically saying that this is gonna be it is kind of like a filtering, but selecting for an odd value, I think. I don't think he fully understands where I'm coming from, but I kind of get where it is coming from. Still kind of hard to think about, but I'm just gonna move on to the other levels. Kind of hard to remember one I just saw. Maybe you should go fast. Problem is that I don't think I'm gonna solve the one that I stopped before because it's very annoying. And the solution, I looked into the solution, is very big and takes a lot of time to produce, so probably gonna do that if I decide to do it. I'm probably gonna do it. But the thing is, you have to do it in order to get to the other levels, and I think I'm gonna want probably to finish the whole thing at some point. I think I'm gonna have to try to copy the solution. It's kind of annoying because it is very complex. I don't remember what pattern this is trying to capture on this level. But it's very similar to the other one that I've seen before. It's basically the same input relationship here. That it like changes the frequency in half, I think. Or yeah. It doubles the frequency on each input. But the output is different. But the other thing that I remember that ChatGPT said is that you can know when you have a fixed point on a circuit if the outputs have if you have two different outputs for the same inputs, and if whenever that's the case, uh, you can't do the normalization on Boolean algebra to arrive at this solution because you need to have this loop pattern on the circuit or to be able to solve it, and that's the reason why you can have two different inputs and the same outputs on the table. I'm pretty sure that this one also looked into the solution. I wish there was an easy way to just like copy the circuit to ChatGPT. If I type down the truth table here, you're gonna understand. I'm just gonna ask you. I'm gonna type down the truth table and ask it to explain, and then move on to the other levels.
I'll treat this as Boolean function synthesis and invariance over the 4 cube, not as gate wiring. Decode the truth table as structure, not bits. You have 4 inputs. The table is written in the standard binary counting order. Let's name inputs A, B, C, D, B, C, D, B, C, D, with AAA the fastest changing, LSB, and triple D the slowest, MSB. AAA, 0, 101 trillion, 10 billion 101 million 10,101. Triple B, 0, 0, 11 trillion, 1 billion, 100 million. This is the canonical enumeration of the 4-dimensional Boolean cube. The output is copy code to 0, 0, 0, 1 trillion, 11 billion. Let's rewrite that aligned with input regions. Already a strong pattern emerges. 2. First invariant, the top half is saturated. For all rows where d equal to and output equal, so one entire half of the 4 cube is filled. That tells you immediately. The function contains the term triple D, or more precisely, triple D is or ed at the top level. This explains why the final gate is an or combining 2 large substructures. 3. Restrict to the subspace d equal to 0 d equal to 0 d equal to 0. Now look only at the lower half, first 8 rows. Let's copy codia BC or out. 0, 0, 0 or 0. 0, 0 or 0. 0, 1. Rewrite that as a Boolean condition. The output is 0 only when fewer than 2 inputs among A, B, C are 1. Equivalently, out equal to and A is the key pattern. 4. The function being tested. So the full function is output is true if at least 2 inputs are true, or if triple D is true. This is why the level is called double trouble. Double equal to 2 simultaneous truths. More formally, A, B, C, D equal to A, B, A, C, B, C, D. This is a 2 of minus 3 threshold function, or id with a bypass input. 5. Why 6 and gates appear. Now map that back to the circuit. Among 4 inputs, the number of unordered pairs is 42, equal to 6 binom. 2, equal to 6, 24, equal to 6. Each and gate corresponds to 1 pair being simultaneously true. Those 6 are Abel and Bab, Akel and Kek, Adel and Dad. But notice, any pair involving triple D implies d equal to and d equal to and d equal to, which already guarantees output tune. So these terms collapse into the same OR region. This is why the ANDs are grouped into 2 ORs of 3 inputs each. It's a spatial factoring of the 6 pairwise conjunctions. 6. Why this is not XOR-like. Contrast with XOR. XOR is about odd parity. This circuit is about cardinality. This is a majority threshold detector, not a parity detector. XOR collapses information. This circuit accumulates coincidence. False means no 2 inputs are simultaneously active. The space is still sparse. True means the system has entered a dense region of the cube. 7. Geometric interpretation, your topology framing. In the 4 cube, single bit activations are isolated vertices. Double activations lie on 2 faces. Triple activations lie in 3 faces. Quadruple activation is the top vertex. This function turns on exactly when the point lies on any face of dimension greater than or equal to 2, or in the entire half space d equal to and d equal to and d equal to. So the circuit is detecting overlap, not difference. That is the dual of XOR. 8. Why the structure must look like this. There is no way to detect at least 2 inputs are true without enumerating pairwise coincidences, ANDs, accumulating them, ORs. This is an irreducible combinatorial cost. The level is testing whether you understand how to go from a truth table to cardinality constraints. How, and enumerates coincidences. How or unions them into regions. 9. The core lesson of double trouble. XOR levels teach structure via exclusion and parity. This level teaches structure via coincidence and density. You are moving from group-like logic, GF, to threshold logic. That shift is exactly what the puzzle is designed to test. If you see the output as the moment space gets crowded, the circuit becomes inevitable.
I'm gonna try to get a bird's eye view. It's very easy to understand conceptually what it's saying, but I'm trying to clarify how this is gonna connect to the other circuits in order to make sense of this. Basically, what it just says is that whenever you have a bunch of AND gates like this, like a convergence point, it's gonna converge the input into a concentrated output. That's how I think about it. The XOR is gonna filter out the differences. Like XORs, when you have a bunch of XORs together, I think it works like an interference pattern on a wave, probably. And the end is the constructive pattern, and the XOR is the destructive pattern of the interference of the inputs. That's how I think about it. But the hard part is trying to clarify like how do all these circuits are gonna connect to the control logic of the hardware, and how does what circuit's gonna make sense of the magnitude of the numbers of the outputs. And that's what matters. It's becoming more clear to me how it works. Yeah, I'll be right back. I'm gonna read this next, and then I think I'm gonna try to go faster on the other levels, the other challenges, and try to get to the point where I stopped, and then probably stop streaming after that. I'll be right back.
At a high level, the two patterns you've been dissecting are not puzzle tricks. There are two orthogonal ways of collapsing high-dimensional Boolean space, and almost all non-trivial digital systems are built by composing exactly these two kinds of collapses. I'll frame this structurally, not historically. 1. The two patterns, stripped to their essence. Pattern A, XOR, parity logic. Invariant preserved, parity, mod 2 sum. Operation. x1, xn. Algebra, linear over GF2. Geometry, partitions the Boolean cube into even versus odd subspaces. Information effect, forgets magnitude, keeps difference. SOR answers. Did something change? Are these equal or different? Is the number of activations odd? Pattern B, and or coincidence, threshold greater than or equal to k. Invariant preserved, cardinality, density. Operation. Algebra, monotone Boolean logic. Geometry, selects high-density regions of the cube. Information effect, forgets identity, keeps accumulation. And or threshold logic answers. Did enough things happen? Are multiple conditions simultaneously satisfied? Is the system overloaded, convergent? These are duals, not competitors. 2. Where XOR parity logic appears in real systems. A. Adders and arithmetic. Half adder. Sum equal to XOR. Carry equal to, and full adder. XOR chains plus coincidence detection. Is how arithmetic detects difference without carry. B. Equality, comparison, and diffing. Bitwise comparison. Equal XOR equal to 0. Hash mixing. XOR diffuses change without bias. Change detection in pipelines. Is the minimum disturbance detector. Error detection and correction. Parity bits. CRCs, linear feedback shift registers. Hamming codes. These rely on the linear structure of XOR. Errors add. Parity violations expose them. D. Cryptography, structure layer, not security. Whitening. Stream ciphers. Masking. XOR is used because it is invertible. It composes cleanly. It preserves entropy while hiding structure. Free, where threshold, coincidence logic appears. A. Control logic and guards. Only proceed if at least two subsystems agree. Trigger if multiple conditions hold. This is literally your double trouble circuit. B. Voting and redundancy. Majority voters. Triple modular redundancy, TMR. Used in aerospace. Safety critical systems. Fault tolerance. Scheduling and resource arbitration. Contention detection. Load thresholds. Saturation logic. These circuits detect crowding, not difference. Neural and analog digital hybrids. Perceptrons. Threshold gates. Activation functions. Threshold logic is the Boolean shadow of analog accumulation. 4. How they compose in real architectures. The important point is not where they appear individually, but how they interleave. Example, addition. For each bit. XOR computes local difference. And computes local coincidence. Or propagates coincidence forward carry. That is, parity plus density. Exclusion plus accumulation. Every adder is an interleaving of the two patterns. Example, state machines. AG/OR. Detects transitions. Encodes toggles. And/or. Enforces guards. Stabilizes state. XOR destabilizes. And/or stabilizes. You need both to get controlled motion. 5. Big picture. Two orthogonal bases of Boolean computation. You can think of Boolean logic as having two bases. Linear, XOR-based. Sensitive to change. Reversible. Algebraic. Compositional. Monotone, and/or based. Sensitive to accumulation. Irreversible. Order-preserving. Stabilizing. Almost every circuit can be seen as linear mixing, monotone collapse, linear mixing. This is exactly analogous to signal processing, mix, filter, threshold. Control theory, error, accumulation, correction. Computation, difference, decision, action. 6. Why Turing complete teaches them early. These two patterns are the first non-trivial invariants you can impose on Boolean space. XOR, invariant under complementation of pairs. Threshold, invariant under permutation of inputs. Once you understand these, adders stop being magical. Comparators stop being mysterious. Control logic stops being ad hoc. You're learning the grammar of digital structure. 7. One-sentence unification. XOR logic detects how space changes. Threshold logic detects when space becomes crowded. Computation emerges from alternating between these two kinds of collapse. That's the bigger picture these levels are training you to see.
Yeah, so I think I understand now. So this is basically testing for threshold. So once the inputs reach a certain threshold, it's going to be true more often, I think. So this is probably used for converting analog inputs into digital outputs, I think. Makes a lot of sense. Okay, so let's go over. This one is just testing to see the numbers, kind of irrelevant. Already went over this. So this is a half adder. It's basically what once represented just said that the sum is going to be XORs. And one thing that I was thinking about is why XORs are used for the sum if they are checking for the difference. But I think it's just because of the composability. Like sum is composing different structures. So I have to measure what's different between them to get the new magnitude, I think. There's another level that is the full adder. This is the full adder. I'm gonna look into the other ones. That's very simple. Counting signal. Zone is also interesting. So this is the same inputs relationship, but the output is different. Maybe this one is interesting to ask again. So the other one was like the same relationship between the inputs, but because the output was different, we used a bunch of AND gates and the OR gates, the one that I just saw. So this one is like a clear threshold. I think that's probably makes sense to ask about this one now, before I ask the full other stuff. Let me think about like what is the main. Actually, I misspoke because I thought this was the output, but yeah, I think that the main thing that it changes is just that it's using 3 outputs instead of 1. But why does this impact the rest of the gates so much? Obviously, it has to be because of the difference. Like it has to be a different output, I think. Like if I converted the numbers, because obviously these numbers here are gonna be just the impulses here. Like I think when the first one is on, it's gonna be 0 probably, I think. And when the second one is on, it's gonna be 1. Third is gonna be 2. The rest is just combinations of them. You can convert this into booleans and then get a similar uh, proof table, I think. But actually not, because it would be different actually, because it would have 2 different values instead of the decimal. So I guess like this is the where it gets confusing, because there's the assumption here of what the impulse means for the circuit. And the challenge here is how to explain this circuit to the. I'm just gonna send the truth table and the name of the level, and then ask to explain what is going on. And ask why do the gates change so much if the inputs are the same. So
This level is a qualitative shift, not a quantitative one. The inputs did not change, but the semantic contract of the output did. That forces a different factorization of the same Boolean space. I'll make that precise. 1. What changed exactly? In double trouble, the output was a predicate. Is the count of 1 second greater than or equal to 2, with a shortcut via D? That collapses the 4 cube onto 1 bit. Massive information loss is allowed. In counting signals, the output is no longer a predicate. It is a measurement. How many inputs are 1? The outputs. Copy-coded are the population count, Hamming weight, of the 4 inputs, encoded in binary across 3 wires. So the circuit is no longer a filter. It is a homomorphism from a multiset to a number. That single change forces everything else. 2. The invariant being preserved now. Let inputs be x1, x2, x3, x4, x1, x2, x3, x4, x1. The function is. This is not Boolean logic anymore in spirit. It is integer addition, implemented in Boolean hardware. The invariant is no longer parity, XOR, or coincidence, and or, but cardinality, with full magnitude preserved. You are preserving how many, not just whether enough. That requires carry. 3. Y XOR, and suddenly appear everywhere. Look at a single bit addition truth table. Absum carry, this is fundamental. Sum equal to XOR. Carry equal to, and. No workaround. This is not a design choice, it is a theorem. So the moment the puzzle asks you to count, you are forced into the XOR, and pair everywhere. That's why your layers look like SOR, and SOR, and SOR, and. You are watching addition being factorized spatially. 4. What the circuit is actually doing. The circuit is implementing a population counter, pop count. Conceptually, pairwise add bits. Add partial sums. Propagate carries. Emit a binary number. But because this is combinational and parallel, the steps appear as layers. Each layer. XOR computes local sum modulo 2. And computes local overflow. Those overflows are then added again. 5. Why the structure is so different from double trouble. Double trouble. Uses and to detect coincidence. Uses or to union regions. Destroys magnitude information early. Counting signals. Must delay collapse. Must root carries explicitly. Must preserve partial sums. In other words, double trouble is monotone logic. Counting signals is arithmetic logic. Arithmetic cannot be done with or alone, because or does not distinguish. 2 inputs are 1. From. 3 inputs are 1. Once you need that distinction, or becomes useless except as a final collector. 6. Why there are 3 outputs. Maximum count of 4 inputs is 4. Binary representation. 0, 0, 0, 0, 0. 1, 0, 0, 1. 2, 0. Those 3 output wires are not 3 answers. They are bit positions in a number. Each output bit has a different semantic role. LSB, parity of the count, XOR of all inputs. Middle bit, second order carry structure. MSB, are at least 4 inputs active. Each bit preserves a different invariant. 7. The deeper pattern. This level teaches. This level is teaching you that Boolean logic splits into linear logic, XOR, and nonlinear logic, and counting requires both in a disciplined alternation. More precisely, XOR tracks value modulo 2, and tracks overflow into higher order structure. Repeated alternation reconstructs integers. This is the minimal embedding of arithmetic into Boolean space. 8. Geometric interpretation, matching your framing. Think of the 4 cube again. Double trouble. Partitions space into 2 regions. Forgets which face you're on. Counting signals. Stratifies the cube by Hamming layers. Layer 0, weight 0. Layer 1. Layer 2. Layer 3. Layer 4. The circuit computes which stratum you're in, encoded numerically. That is a much finer quotient of space. 9. Why the game places this level here. This is the moment where XOR stops being difference, and stops being coincidence. And both become arithmetic primitives. After this level, adders will feel inevitable. Comparators will feel obvious. Counters will feel mechanical. You're crossing from logic as predicates to logic as measurement. 10. One-sentence synthesis. The structure changes because a single bit predicate can throw information away, but counting cannot. Preserving cardinality forces the circuit to explicitly represent addition via XOR, sum, and carry, revealing the arithmetic skeleton hidden inside Boolean logic. That is the invariant this level is drilling into you.
Well, test to see if I do this another way, because I think this way is kind of weird here. I think I copied this from a solution, so I'm gonna see if I connect directly. Yeah, but I think it's probably not gonna work. They need to be. Maybe it does work. Yeah, it does work. So this pattern here was the half adder on the other level. I think I could do the same on the other here as well. think about this. This one might be different though. Oh no, this one is the same. This one's already correct. There half true. So we have two half adders here. This I understand intuitively what it's saying to me, what ChatGPT is saying. So basically, when you combine the XOR gives you module 2, arithmetic, and the AND propagates the accumulation of the module 2. So the final output encodes the decimal value because of that. But I don't understand, the nuance is not very clear to me. Like, what does it mean, fundamentally speaking? I should have done this with different color of the wires, because now it's very confusing to understand like what's each one is connected to. But I think that this one is gonna go here. So like it's basically crossing the outputs on each level from the previous one. It starts off as a half adder in the beginning. I have two half adders. Then the second layer crosses the outputs, I think. And from the first to the second crosses the outputs and then crosses again here on the middle. I don't understand like what does it mean to do this. And why it's not symmetrical. I think the reason why it's not symmetrical is probably because it has to increase the value when it's going to the right. That would be my assumption. So like when you increase the numbers is by definition asymmetrical because it has to encode the relative magnitude, I think. But I'm not really sure if that makes sense.
You're stuck exactly at the right fault line, the point where Boolean circuits stop being spatial pattern detectors and start being number systems. I'll answer by collapsing the confusion into invariance and necessity, not wiring folklore. First, the asymmetry is not accidental, it encodes significance. The most important thing to internalize. Binary numbers are asymmetric by definition. Each output wire does not represent the same kind of fact. LSB, is the count odd? Next bit, how many pairs exist after removing parity? Next bit, did overflow exceed capacity of lower bits? So expecting symmetry is already a category error. SOR and appear symmetrically within a bit slice, but between slices, there must be directionality. That directionality is carry propagation. 2. What the first layer really computes, not partial sums. Take 4 inputs, A, B, C to B, C to B, C, D. First layer computes XORs, local parity of pairs. ANDs, local coincidence of pairs. Crucially, SOR answers, is there 1 here? And answers, is there 2 here? Each pair is reduced to a 2-bit number. A plus 0, 1, to a plus bin 0, 1, encoded as XOR, bit 0, and bit 1. This is already arithmetic, just compressed. 3. Why second layer must reuse both XOR and outputs. Now you have 2 2-bit numbers. You must add them. Binary addition rule. Size sum carry 0 0 again. Sum equal to XOR. Carry equal to AND. So the second layer is not arbitrary wiring. It is enforcing the algebraic decomposition of addition. This is why the same signals feed both XOR and AND. Every XOR has a sibling AND. That's a theorem, not a design pattern. 4. Why the third layer exists at all. After adding 4 bits, maximum sum is 4, 1002. Carries can stack. So you must add carry from previous addition. Merge it with existing higher order bits. That is what the third layer does. The third XOR computes the parity of accumulated carries and sums. The third and computes whether 2 carries collide, overflow into the next bit. You are literally watching bit significance emerge. 5. Why, or appears only on the right side. Or is used only when information no longer needs to be distinguished. On the MSB, any carry implies the bit is 1. There is no higher bit to propagate into. So, MSB equal to carry 2 carry 3 text, and below that, XOR is required to preserve parity information. So the asymmetry is caused by boundary conditions, not design choice. 6. Why signals fan out into both XOR and AND. This is the core insight you're missing. A single Boolean wire represents a bit, but a bit participates simultaneously in sum and carry. So, any bit entering an adder must contribute to sum, contribute to carry. Hence, 1 wire, XOR. Same wire, AND. This is not duplication of meaning, it is orthogonal projection. 7. Why this propagation creates integers, and not something else. Integers arise because XOR preserves value modulo 2, and preserves overflow. Repeated composition reconstructs positional weights. This is exactly how binary numbers are defined. There is no alternative mechanism that preserves all cardinality information, remains combinational, uses Boolean primitives. If you want exact counts, you get this structure. 8. Isn't the encoding arbitrary? This is subtle, but important. Yes. You could label 100 as 2. Or invent gray code. Or use unary. But the circuit is not arbitrary. The encoding is determined by closure under addition. Binary encoding is special because value, that is the invariant. Most encodings do not preserve that. So the meaning is not imposed by humans after the fact, it is forced by the algebra the circuit implements. 9. Bigger picture, what you are actually learning. This level is not about gates. It is about this realization. Arithmetic is the unique fixed point of Boolean composition under counting constraints. Once you demand exact cardinality, composability, locality, you are forced into SOR for parity, and for carry, asymmetry for significance. Everything else is decoration. 10. One sentence to anchor everything. The circuit looks asymmetric and layered because it is not detecting patterns in space anymore. It is embedding the algebra of natural numbers into Boolean logic, and that algebra is inherently directional, carry-based, and significance ordered. Once you see each layer as a parity, propagate overflow, the wiring stops being mysterious.
I'm gonna need more time to think about this. Probably gonna ask more questions off stream. Because I understand what he's saying, but there's still deeper questions I wanna ask about it. There's still a lot of them. Okay, so here the sum is the two XOR connected. So the ends of the two puts carry over. It's kind of hard to understand why the first two inputs are ended. Not sure if that's the correct way to say. Why this first two go directly through the end for here, and this other one goes through the XOR first, and then the end. So I think I'm just gonna ask that on this one. It's easy to understand the conceptual level, but it's hard to clarify the nuances of what exactly does it mean. Series obviously is gonna say that the XOR is the sum and the end is the carry. But I don't understand, like if I had to build this from scratch, I don't think I would be able to do it yet. Maybe I would, but it would take some time, I think. I probably wouldn't come up with this solution exactly. I think I would try to XOR all three components first, then connect them with an AND gate later somehow. That's probably the first thing that I would try to do. I'm trying to clarify, like, but it makes the thing that makes this hard as well is the relationship between the binary and the decimal. Because binary addition is kind of confusing. Like the carry of the binary addition, confusing. Because I think it's slightly different than the decimal. Because when you have a 2 carry, it becomes a 1. Like, because it becomes the, or yeah, when you have a 2 carry, it becomes a 0 actually. And then it just goes over to the next square, I think. Because the squares have more called magnitudes. So I think that this is what's another thing that makes it hard to think about, because I'm naturally thinking about the decimal addition instead of the binary one. But I think like here is the same, like this shoe is the same pattern of the half feather that I saw before. Well, I think that this one, like, is selecting the odd value of this, works as a sum on Boolean. Then this one carries. This would be the result of the sum here. And this one is the result of the carry. So this carries the sum of this with the third input. I think that this part here is just propagating the carry of the first sum, probably. Actually, it has to be the two, actually. I understand now. So like the first level carries the first sum, the second signal carries the other one. Then the sum goes directly here, and it propagates through this. The sum of these two propagates through here, I think. Yeah. So the sum of these two propagates the carry through this signal, and this other the third input input propagates the carry of the sum of these two, or the result of this with this one. Yeah, that's what's going on, I think. So this one is these results, and then this one, and then it propagates the result here to these inputs. Then the R is just to connect them together. So let me think about how to ask this.
You are circling the exact hinge where Boolean logic becomes arithmetic. The confusion is not accidental, it comes from trying to hold two interpretations at once, difference versus sum, without the invariant that unifies them. I'll resolve that directly. XOR is not difference or sum, it is addition in GF, 2. Start here, cleanly. AB equal to plus B. This is not an analogy. It is a definition. The field GF, 2, has elements, 0, 1. Addition table. Plus 1,001,110. Compare with XOR. They are identical. So XOR is addition, just addition without carry. Everything else follows from this. 2. Why difference and sum collapse in binary? In integers, sum and difference are distinct. Magnitude matters. In mod 2 arithmetic, 1 plus 1 equal to...
I think it is confusing because of the true thing. So whenever I have true inputs that are 1, the result's not going to be 1. It's going to be true, so it carries over. The result is 0. That's why it's confusing. So the XOR works as a sum because the relationship is what the sum produces each time. But then you need the end to propagate the results, because otherwise you would lose the information that the previous was true and not 0. That's the part that I think, yeah, now I think it is clear. I think that's the part that I'm always confused by. Because when you have true ones on a Boolean sum, it's going to be true the result, and you're not going to have the 1 as the result. You're going to have 0, and then the 1's going to propagate through the carry. So that's why it's confusing. So when you have the ends, it's like chaining the connection between the previous sums. I think I understand now.
1 plus 1 equal to 0. 1 plus 1 equal. They collapse to the same operation. So are answers simultaneously. Are they different? What is their sum modulo 2? These are not two interpretations of XOR. They are the same invariant viewed from different domains. 3. Why binary addition splits into XOR plus and. Take normal integer addition of 2 bits. A plus binary representation of the result needs 2 bits. Sum bit, LSB. Carry bit, MSB. Decompose. A plus equal to, AB plus 2. This identity is exact. XOR gives the low order bit, and gives the high order bit. This is not a circuit trick. It is arithmetic factorization. 4. Why, and is the only possible carry detector. Carry happens, IFF. A plus, that predicate is, and. So yes. The carry gate must be fed by the same inputs as the XOR. If you detect carry from different signals, you are computing a different sum. Carry is not optional metadata, it is the part of the integer that XOR throws away. 5. Now, the full adder, step by step. Inputs. B, data bits. Sync and syn, carry in. Step 1, add a plus B plus BA plus. 1 equal to OBS, 1 equal to A plus BS 1 equal to OB. 1 equal to ABC, 1 equal to A land, BC 1 equal to AB. This gives A plus B equal to.
Yeah, so what is happening is that this input here, like whenever this is on, let me think about this. This one is determining the sum of the other one, obviously. So when it's on, it's gonna be like 1, the sum. So this encodes the carry because it is the same input used by this one, which encodes the other sum. So it wouldn't work if the input wasn't connected to the other sum. Because whenever this is on, this one has to be off in order for this to be 1. For this to go through. Or is that? Yeah, it's kind of confusing still. Yeah, so if this is on and this is on, then but wouldn't that mean that you have like this would be 0? But this is the weird. But I think that that's where the carry gets AAA, I think. Because if this is 1, then it means that these two inputs were summed. And if this is 1, doesn't it mean that you have like another sum between this input and the other two? So this would be 1, and this would be 1, so this would be 0, and then it would carry over here, I think. Yeah, because both of them are 1. Yeah, makes sense. So when this is 1, it means that it sums this two, and when this is 1, it means that it is supposed to sum this with the other one, which means that this is going to be 0, and then you're going to lose the information because you don't have the 1, so it carries over. Yeah, makes sense. You can understand now.
A plus B equal to. Step 2. Add carry in. Now add S1 plusins, 1 plus Cns 1 plusin. Final sum. Carry from this addition. 2 equal S1 sing 2 equal to S1 lend. C in C2. Step 3. Combine carries. Total carry out happens if either ABB both 1 or exactly 1 of ABB was 1 and carry in was 1. So, count equal to TLC1 C2. That's the full ladder. Nothing arbitrary. Nothing heuristic. 6. Why the sum of 3 inputs is implemented with 2 XORs. You said.
So I think that the XOR answers, is there a difference in this space? And the AND answers, is this difference supposed to accumulate on the, supposed to fill up the space on the AND results or not? That's the, so obviously subtraction is not gonna fill up the space, so the AND is not gonna propagate the results or the carry, because then the magnitude doesn't increase. But if it is supposed to accumulate on the end result, then the end carries the meaning. So the end is like the operator for scale of the magnitude of the input, and the XOR is just asking the question of whether or not there are differences on the space of the on the input space. And I think that this has to be the case because scale is just a matter of the observer. So everything is relative, obviously, so as above, so below. So the scale of things is going to be always related to the observer. Something looks bigger. Like you can have something that is the same size, but it will look bigger for an observer that is smaller than the other one. So the end is like propagating the magnitude of the scale of the difference. And you need the difference, because if you didn't have the difference, then you wouldn't perceive the boundary between what the thing is and the environment. There's always going to be a difference between the two. It's like a wave function. So it's like the double slit experiment. So either you have two constructive waves or two two destructive waves. And the pattern you see on the result is going to determine the magnitude of the relationship between the waves. So the XOR would be like the slits on the double slit experiment, or it would be like measuring the interference of the wave patterns, and the AND propagates the accumulation of the constructive patterns.
I view this XOR as summing all 3 inputs. Correct, but precisely. So that XOR chain computes the least significant bit of the integer sum. But integers have higher bits, those are the carries. Hence, the AND gates. 7. Why XOR must feed both XOR and downstream. This is the critical structural insight. The intermediate sum bit, S1, 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 contributes to the final sum. Also contributes to carry generation. So it must be fanned out. This is not duplication of logic, it is decomposition of one integer into orthogonal components. Think of it this way. Extracts parity. And extracts overflow. Both are projections of the same quantity. 8. Why this produces integers, not just bits. An integer in binary is. Each full adder computes one coefficient BB, and one carry into bi plus un BB plus 1 bi plus 1. So the circuit is literally.
I think that the next question that I'm going to ask is, why do you need difference to have addition? The problem is, like, based on the current setting I have on ChatGPT, I don't think it's gonna give me like a general picture, like from physics, fundamental physics perspective. It's just gonna talk about the Boolean algebra, I think. So maybe the answer is not gonna be very good. I think this is the main thing that I'm trying to contemplate right now. Like, why when you use an OR gate, it doesn't encode. I think that this is the biggest thing that's the biggest reason why it makes it confusing. Because I think if you're coming from the decimal point of view, it would make more sense that the OR gate is the one that does the sum, because it obviously connects the whole structure together. So the fact that this is not the case is the thing that is weird. I think that's what I'm gonna ask next. Why is this the case? Why when you filter or when you select for difference, you have the sum, and not when you select for the union? And I'm gonna ask what happens if you select for the union instead.
Literally constructing positional weights. The reason the output means an integer is not human convention. It's because value out. That equality holds structurally. 9. Deep unification. This is the core answer. XOR is used for difference, parity, sum bit. Because all three are the same invariant in GF, 2. Whether the total contribution flips the least significant bit. And is used for carry because carry is exactly the information lost by reduction mod 2. Binary arithmetic exists because integers equal to parity plus carry of carry plus. The full adder is the smallest circuit where this recursive structure becomes explicit. 10. One sentence to lock it in. XOR is sum because binary addition is XOR plus carry. XOR computes addition modulo 2 and detects the overflow that modulo arithmetic discards, and chaining them reconstructs the integer exactly. Once you see XOR and AND as the two projections of integer addition, the full adder stops being mysterious and starts looking inevitable.
I think after this one, I'm gonna stop streaming because I'm already very tired from thinking about this. Then I'm probably gonna ask more questions off stream. I think probably off stream I'm gonna try to solve the annoying level to get over with. Then look for the solutions of the other levels. Like I said before, like I don't really care about solving each level. Just looking into this game just to understand or to review more the concepts of how the hardware actually works on fundamental principles.
This is the right question. It forces you to confront why arithmetic embeds into Boolean logic the way it does, instead of taking XOR on faith. The short answer is, OR destroys information that addition needs, while XOR preserves exactly the right invariant. I'll unpack that precisely. 1. What sum actually means, structurally. A sum is not union. A sum is a homomorphism. A plus plus equal to plus. It must be associative. Compose cleanly. Allow carries to be factored out. Preserve invertibility modulo carry. So the question is not what feels intuitive but, which Boolean operator is a valid projection of integer addition? 2. OR is monotone, addition is not. Look at OR. ABA or B 0000. 11 million. Key property. Or is idempotent. 1 1 equal to 11 lar. 1 equal to 11 1 equal tune. Now compare with addition. Once 1. Or collapses multiplicity. It answers. Is there at least one? Addition answers. How many? The moment two 1s appear, or throws away the distinction between 1 and 2. That single fact already disqualifies or as a sum operator. 3. XOR preserves multiplicity modulo 2. SOR table. Key property. 1 equal to 0, 1 plus 1 equal to 0, 1 1 equal to 0. That looks wrong only if you forget the carry. What SOR is doing is counting contributions, then reducing mod 2, without collapsing structure prematurely. It preserves parity, reversibility, linearity. Those are exactly what addition needs at the lowest bit. 4. Y or plus, and cannot simulate addition. Try to decompose addition as a plus b equal to a. Test it. Equal tune, b equal tune, or equal to 1, and equal to 1. Result equal to 1 plus 2 equal to 3. So, or overcounts. Why? Because, or already counted at least 1 and counts 2, so the second contribution is duplicated. This shows and are not orthogonal projections of addition. SOR and are. 5. Orthogonality is the key word. For addition, you need two components. Low order bit. Overflow bit. These must satisfy. A plus b equal tof, ab 2 plus g, ab a. Only one pair of Boolean functions satisfies this for all inputs. F equal toxorf, equal to xorf equal toxor. Equal to eng, equal to eng equal to end. This is not design choice. It is algebraic necessity. Or fails because it overlaps with and. It double counts. It is not orthogonal. 6. What or actually computes, and why it feels intuitive. Or computes. Max. That feels like union because it's set theoretic, not arithmetic. Or is good for availability, reachability, permission, existence. But addition is not existential, it is quantitative. Union answers. Is anything present? Some answers. How much is present? Different invariants. 7. What happens if you build a full adder with ORs instead of XORs? Let's do it explicitly. Replace sum equal to XOR, or carry equal to, and stays. Then, sum equal to absin or blor kin absin. Carry equal. What does this compute? Behavior. Sum bit is 1 whenever any input is 1. Carry bit is 1 whenever 2 or more inputs are 1. This is not addition. This is a threshold detector. Sum bit approximately equal to greater than or equal to 1. Carry bit approximately equal to greater than or equal to 2. That's a population count predicate, not arithmetic. You get monotone logic, not numbers. 8. Y XOR is the only gate that survives layering. When you stack layers, SOR preserves linearity and propagates overflow or destroys magnitude. Try chaining ORs. Once a bit becomes 1, it can never revert. Information monotonically collapses. Addition requires cancellation. 1 plus 1 equal to 0 carry 1. Reversibility modulo carry. Composability. Only XOR allows cancellation. 9. The deeper connection you're really asking about. Why does difference encode sum? Because in binary, difference and sum share the same least significant bit behavior. That is not true in base 10. It is true in base 2. Binary is special because plus 1 equal to, so parity, difference, and addition collapse into one operation. 10. One sentence synthesis. OR encodes existence and collapses multiplicity, so it cannot support arithmetic. XOR encodes parity and preserves linear structure, making it the unique Boolean projection that can serve as the sum bit of integer addition, with and recovering the overflow it discards. Once you see orthogonality instead of intuition, XOR stops being surprising, and or stops being tempting.
I'm just gonna briefly look into the other levels, and then stop streaming. Probably very tired. These ones are not interesting, and not interesting as well. It's just adding the 2 bytes here using this adder gate that we build. This is the full adder that we build there on the other level. Other race. Just negating the value. Not interesting as well. Like a lot of these are probably more foundational things you need to know before moving on. And these ones are this is just circular dependency. These are related to the time. This delays 1 tick, this thing here. Very odd ticks. Interesting as well. Also, this level is just to show that the bit inverter is the same as an XOR. This one with selector. So using the switch from the previous level, you have this gate here. It works as an enable. I think it's used, but this is not used on the decoder, but it is used, I think, on for the latch probably, for the level where you save. They did the level in a way that you have to use the switch instead of building an SR latch or something like that. And I just look for the solution. Yeah, so this is just showing. So I think that this, what the name of this? I think it's a try bus. So this pattern here is the one used on the components to connect the outputs of the bus, which is wires that connect all the circuits of the computer, to other circuits. So this allows the, for example, the arithmetic logic unit to not consider every output that is going through the bus. It's only gonna consider that output that the bus is sending, the signal that the bus is sending, whenever there's a selection logic that makes this circuit here be true. I think that's what it's used for. I think the name is Tribus or something like that. Let me see. Maybe there's another name that I forgot. A tri-state. Yeah, tri-state bus. Or three-state. But I'm not really sure if this one is the three-state or not. The one that I have here. But since the name is the bus, obviously I think there is something related to this. Yeah, whatever. At this level here is the one that's for memory. So this is the way you're supposed to solve. But the way that's usually starts is based on the SR latch gate, which is a gate that has like a cross pattern, kind of. That the output of one of the gates goes as the input of another. And you can use either two NOR gates or two NAND gates, if I remember correctly. Then you have variations of the SR latch that works based on the clock, which I think is D flip-flop or something like that. But on this game, they chose to kind of force this solution here. It's different. Maybe there are other solutions, but I didn't spend the time trying to figure out. This delays by 1 tick. Output. I'm not sure if that's very interesting as well to ask questions to ChatGPT. Yeah. Maybe I'll ask later. So this is the memory for the saving gracefully. Basically becomes another gate. This is also very simple, I think. Just connecting the save input on here as the enable, I think. And the value here. Yeah, so this is the save and this is the enable or something like that, I think. Don't. Yeah. This is the save and this is the load. If I miss any. Maybe this one I wanna ask GPT, what is this? Let's know. So this one is a decoder, and it's basically just encoding all the possible combinations of these 3 inputs here into the 6 or into these 8 outputs. And I think this is used for mux multiplexer. I don't remember really well, but I think it has to do with control logic. I'm pretty sure. Maybe it's not. I think that a mux is a decoder with selectors, but I don't remember really well. And from what I remember, a mux is the encoding of a function on logic gates. Yeah, so it's probably a decoder with a selector. Selector, like the name says, is gonna select which outputs or which input is means something or not, which is different than being turned on or not. Like if the selector is off, it doesn't matter what the input does. It's not gonna count. And if the selector is on, then the input counts. So it could be either 0 or 1, from what I remember correctly. Or from what I remember. Not sure if it is correct. So I think that this probably is used for functions at some point. And the little box is the one that I stopped. I think that is very hard. Oh, looks like I passed. Oh no, it was another one that is much bigger, I think. This one I just copied the solution from somewhere, also because I like too complicated and didn't want to spend a bunch of time thinking about it. With 4 bytes of memory in this limited. So I assume that this is going to be used for the RAM or something like that. Just saves memory. Yeah, the counter is the one that was very. I think the solution is very big. So I didn't want to do it. It's also going to be annoying. I think this one is from a previous solution that I had. I went almost to the end, I think, before, and then they updated, so the solutions got, some of them got out of date, I think. But they still show up on the schematics. So it looks like this old solution still works. I'll have to solve this again. Or maybe it's because I removed some gate here. Probably a full weather, I think. Because so I think this is an out data solution.
This level is a conceptual pivot, not a new Boolean trick. It is called the bus because it introduces shared wires and mutual exclusion, but it does not yet implement a true tri-state bus. It implements the logical precursor to one. I'll be precise about what it is not, and why the structure looks the way it does. What you are actually looking at. You have 2 byte inputs, multi-bit values. 2 1-bit control inputs. 2 outputs. 4 switches, gates that conditionally pass a value. 2 NOTs. No feedback, no storage. This is not arithmetic. This is selection. Formally, the circuit computes. Out equal. That object has a name. 2. This is a multiplexer, MUX. Specifically, a 2-to-1 multiplexer. Operating on a bus, multiple bits in parallel. The Boolean form for 1 bis equal to SA, SB. Your circuit is implementing this expression bitwise, but the game hides the bitwise replication by treating bytes as atomic. This is why. One switch is enabled by S. The other by. Both feed the same output line. 3. Why it is called the bus. Because this is the first time multiple producers share a wire. A bus is not many wires. A bus is a shared communication medium where only one source is allowed to drive a line at a time. This level introduces that invariant. Not electrically yet, logically. 4. Why this is not a true tri-state bus yet. A real tri-state buffer has 3 output states. 0. Your circuit does not produce Z. Instead, it enforces. Exactly one source is active. The other is forcibly silent via gating. That is logically equivalent to tri-state under the assumption of perfect exclusivity, but implemented with and/or logic instead of impedance. So, Conceptually, yes, this is bus logic. Physically, no, this is not tri-state signaling. Pedagogically, this is the step before tri-state. 5. Why the knots are essential. The knots guarantee mutual exclusion. Let selector be S. One path is enabled by S. The other by is invariant. S. So it is impossible for both byte inputs to drive the bus simultaneously. This invariant is the definition of a bus. 6. Why switches instead of gates. The switch primitive is doing something important conceptually. It does not transform data. It only permits or blocks it. This separates. Data path. Control path. That separation is the entire reason buses scale. Arithmetic circuits entangle data and logic. Bus circuits factor them apart. 7. What would go wrong without exclusivity? If both switches could be on, two drivers would attempt to set the same line. In logic terms, or would merge values incorrectly. In hardware terms, contention, undefined behavior, or damage. So the knots are not convenience, they are safety constraints. 8. Relationship to real CPU buses. In real systems. Registers. ULIS. Memory. I/O devices. All share buses. They do not or their outputs together. They either use tri-state buffers or are time multiplexed through muxes as here. Your circuit is exactly the mux-based bus model. 9. Why the outputs are 2 wires, not 1. You have 2 outputs because the bus is multi-bit. Each bit is independently multiplexed. But semantically they move together. That's what makes it a bus instead of just a signal. 10. What invariant this level is teaching. Previous levels taught. Parity. Coincidence. Counting. Arithmetic. This level teaches. Shared structure requires control, not computation. Or more concretely, data does not decide when it moves, selectors do. This is the conceptual foundation of buses. Register files. Instruction decoding. Memory addressing. Microarchitecture. 11. One-sentence synthesis. The bus is teaching you that a bus is not a wire but a contract. Many potential sources, exactly one active at a time, enforced by complementary control signals. The circuit is a multiplexer that realizes this contract logically before tri-state signaling is introduced physically. Once you see that, the level name stops being metaphorical and becomes literal.
Yeah, I'm gonna stop here because I'm already tired. Probably next time, either I'm going to try to, or just look into the solution. I'm not gonna solve this myself. I'm just gonna look into the solution, or try to solve. If I can't find the solution, I'm gonna try to solve with ChatGPT. So either I'm gonna do this on stream next time, or I'm going to already have the solutions and then go over like I did today. I think I'm gonna try to get this time probably. Yeah, I wanna see if I can do everything, but it might take too much time. But I think I'm gonna try to get to the final level to see the assembly. It's kind of annoying because I don't wanna. Some of these levels are just like manual work and not really any, like you don't learn anything, just about trying different stuff. But yeah, so I'm gonna stop here. Next time probably gonna continue with this thing here. Either that or I'm going to follow the, I think I did a list of projects or exercises to do on stream to study stuff. Next time that's what I'm gonna do, so see you then.